First, I would like to address a question which has been on my mind for a long time. Will we reach artificial general intelligence or human-level vision, for that matter, as a result of sweat or of genius, as decades of hard work, or as a result of a breakthrough? I'm adherent to the El Dorado hypothesis that there is a breakthrough to be made. And here are my arguments. We deliberately raise our kids in very simple and very stable nurseries. And after a mere 2 or 3 years, they are able to grasp the reality of their immediate environment. They can speak, they can act purposefully, and they can learn by single inspection. You show them a remote control once, and they know them all, independent of color and shape and so on. My second argument is this here. To note down the wiring diagram of the cortex, it needs a terabyte. And this is constructed on the basis of 1 gigabyte of genetic information, probably much less, and can be trained with the help of 1 gigabyte of virtual reality nursery. I believe that is possible. This is 6 orders of magnitude difference. And this is a very strong message because it says the brain is dominated by regularity. This is a quarry for theoreticians. You can think it out. You don't need to do connectomics. What is the measure of progress in artificial intelligence? I would like to formulate it as the scope issue. I remember the time when a decent PhD thesis in computer vision worked on one single image, and the algorithm would fail on the next image. We are much further along now because our systems work on whole benchmarks. But we have a long way to go to systems that are completely robust in large contexts, in contexts we haven't even thought about ahead of time. So what is making it difficult to increase the scope of systems? And the reason is clear. It is the variability of actual scenes that surround us. They change in all these different submodalities, starting with camera parameters, with illumination, with the agenda, with the gist, color, material, texture, and so on. So progress will have to be made by making explicit the representations of all these aspects separately from each other, taking into account the interactions between them, and come up with explicit models of individual aspects or aspect fragments. I think these are very obvious points. So a vision system has to take this shape. It starts out with visual input, but it decomposes the input into all these different aspects, links them up with each other. We'll come back to that. Computer graphics is showing a way. In a mere 15 or 20 years, they have shown how to construct realistic-looking scenes, and you all know about how they do it. They have separate subsystems for all these different aspects, like shape only, texture only, illumination only, movement, and so on. And they compose images out of these with projection patterns which are highly regular. I know computer vision is more difficult due to the ambiguity problem. I will come to that. So what is standing? One point I want to make about efficient learning. And I would like you to compare that to deep learning. Each aspect has to be learned independent of the others. So if you want to learn about shape, disregard color, position, size, illumination, and so on, then you have lots of opportunities to learn about a specific shape. And the same way for all the other aspects. Don't look for all the combinations of all the aspects to find your samples. This will cut down the amount of data needed for training by many, many orders of magnitude. Now, the goal function of a vision system has to be consistency. That is, the ability of subsystems of some aspects to predict the others, and all of them together to predict the next frame. This is called minimal free energy by some people. This is not a new idea at all. This is very different from deep learning, where the goal function is predicting human responses. This doesn't need direct human interference. Now, what is standing in the way? I think it is computer vision's Babylonian confusion. Computer vision algorithms have been, for the different aspects, have been developed independently of each other. They are very disparate in terms of mechanisms and data structures, and so it is very difficult to integrate them with each other. What is badly needed, I think this is a real showstopper, we need a coherent data and process architecture that makes it natural and easy to integrate all the different aspects with each other. So what is that data structure? I will come to my answer to that question. I will not just leave you with a question. The neural code. Our brain does it, of course. When we look at a scene, when you look at this scene, it is created within a tenth of a second or so in your mind as a construction. The scenes that we experience are, of course, constructions that correspond to the reality out there. And that poses the question, how does the neural tissue in our brain achieve it to generate this and other mind phenomena, like everything you hear or feel or do? Here is my answer. I have to be very brief. It's just one slide. I had two companies which essentially were based on a face recognition system. Elastic bunch graph matching was the word. We know that the images of an object or of a face enter our brain as a two-dimensional texture, the left part of the image. These texture elements, neurons, are laterally connected. Primary visual cortex is dominated by lateral connections. So they enter our brain as a network, as a net. And I claim a face is to be recognized with reference to a model in another part of the brain, the fusiform complex in our brain. And the decision to be taken is the model homeomorphic to the input? Homeomorphic meaning the same texture elements with some precision in the same arrangement, meaning with the same connectivity pattern. In order to make this decision, you need a set of connections which are structured in terms of neighborhood preservation, the oblique lines here. So this whole process is staged in terms of network fragments, which can be composed into a consistent network. Consistency in the sense of alternate pathways help each other. Now, in this picture, it is only spoken of texture. You have to have other aspects like depth and reflectance and motion patterns, all coming together into a consistent picture so that you get very reliable recognition. I would like to draw so my answer to the question, what is the neural code, is you have network fragments, structured pieces of network that are networks that can be constructed by the system itself by a process of self-organization, that are stabilized by self-interaction of networks. These networks can be activated at an eye blink as quickly as you think or as you look. They combine into larger networks, into comprehensive networks. And I would like to draw your attention to the fact that the decision taking place here is not done by a single unit, but is a collective event. Several networks fitting together, thereby decide, construct the solution on the spot. It could be a completely new solution. It could be a creative first act in many cases. So what I plan to do in my company, which is to start, say, in August, is to fulfill this bill here, understand vision as a process of interacting aspects. We all know that the difficulty of vision in distinction to computer graphics is that the input image gives you enormous ambiguity in terms of the aspects. And this ambiguity, this cloud of ambiguous data, is to be collapsed within a tenth of a second by reducing the activity onto those constellations of features that are consistent with each other, meaning that form parts of network fragments that you have previously learned. That is my answer to the vision problem. And I think this is the framework in which it is to be solved. If you are intrigued, contact me. I'm looking for talent. I'm looking for capital. Thank you.